So this is the Impulse Momentum Unit 4 review guide and how you would go about solving all these things. So first off, you get the first page to kind of list things you should be able to do, keywords you should know about, and objectives. So then down at the bottom, objectives. Down at the bottom, we have all the possible equations you might need. Remember now, each of these P's is an MV. So if you want to write, you could almost rewrite each of these equations as like M1, V1, M2, V2, M1, V1, M2, V2, but finals and initials. So remember, each of these is a mass times a velocity for a collision. And so you could, and I've seen it rewritten like that, where you have MV plus MV equals MV plus MV, or MV plus MV equals big M V because they've stuck together, or big MV because they're stuck together and then they explode apart for an explosion becomes MV1, MV2. Anyway, so these are all the equations. You definitely want to have these on your equation sheet. All right, multiple choice. So, which of the following involves a change in momentum? So momentum is both mass and velocity. So if an object's mass or its velocity, or both, change, then it's a change in momentum. A bowling ball rolls down the lane at a constant speed. No and no. A car coasts down the hill at a constant speed. So sure, it's going downhill, but it's going at a constant speed. Not changing mass, not changing speed. Nope. Skydiver descends with terminal velocity. Terminal velocity is constant speed, not changing mass. And a spacecraft speeds up as it approaches the moon. Well, this is actually losing both mass and velocity. Spacecraft is using fuel, which is lowering its mass, and it's speeding up, which is increasing its speed. So this is D. D is definitely a change in momentum. How does the momentum of an object, its velocity, how does the momentum of an object change if velocity doubles and its mass also doubles? Well, since it's m times v, if I double this number and I double this number, that's going to be 2 and 2, which will be 4 times bigger. Let's find it. Quadruples, B, momentum quadruples. All right, so batter hits a baseball back to the pitcher. Well, if we glance at this picture or just think about the direction that it's going, this would be a positive velocity, thus positive momentum. This way. This would be a negative, since it's coming back, they hit back at him, negative velocity, negative momentum. All right. Batter hits basketball bat, same speed. Yep, so same speed, so same amount, different directions. Which of the following is true? The momentum of the ball is the same before and after. This is the one, A, that everybody thinks. Oh, same speed, same momentum. But momentum is positive and negative. So it's not the same momentum. It's actually the same magnitude, but different directions. So let's see if we have that. Ball's magnitude is greater after. Nope, same speed, same magnitude. Magnitude is less after. Nope, same speed, same magnitude. The magnitude is the same before and after it hits. Yes, the magnitude is the same, but the momentum itself is not. So now we got D. All right. Pool or billiard balls. These are these circular balls. Obviously circular, but the ones you play pool with. When two billiard balls interact in an isolated system, this just means closed system, only consider those two, the momentum of each ball is conserved. No, they can transfer their momentum between each other. The total momentum of the system is 0. Nope, if they're, one starts out moving or something, it doesn't have to be 0. The total momentum of the system is conserved. This is sounding like it's going to be true, especially for an isolated system. Whatever total you start with is the total you end up with. Let's see. The total momentum conserved only if the balls move in opposite directions. Nope. Total momentum in an isolated system is always conserved. C. Small marble collides with a billiard ball that is initially at rest. Which of the following is true? So I've got a small hitting a large. Momentum of each object increases. No, this one's going to go down. It's going to lower its momentum to increase the large object. So the small is going to slow down to increase the large. The momentum of each object decreases. No way. When the marble hits the billiard ball, it's going to make it move. So that's going to increase that one. The momentum of the billiard ball increases, yep, and the momentum of the marble decreases. This one's sounding good, and that would conserve, right? If one increase one, the other decreases. Total momentum before and after is 0. Nope, that one, the marble has momentum, therefore it's not 0 before and after. C is the right answer. All right. A billiard ball moving at 2 meters per second strikes another of equal mass. The first ball stops. Okay, so it had some momentum, p, before, but then it stopped. All went away. It's now 0. What is the velocity of the second ball after the collision? Well, since they are the same momentum, that are same mass, then if it has the same momentum, because the other one stopped, then it needs to go the same speed. All right, question 7 through 9. I got 2 skaters, and they're going to push apart. So 2 ice skaters stand together on a frictionless surface and push the cart apart, or push apart. After they push apart, their final momentum are. Well, it looks like there's 0 here, and they both have momentum here. So let's see what they're equal in magnitude and direction. Nope. They may be equal in magnitude and momentum, maybe not same velocity, but same momentum, but they're not the same direction. Equal in magnitude, opposite in direction. Yep, that's sounding pretty good. B. Again, this is the momentum of them. In the same direction, but possibly of different magnitudes. Nope. Equal magnitudes. Since 0 before, these 2 momentums have to cancel, so they need to be the same amount. Opposite directions, different magnitudes. Nope, it's going to be B. Same magnitude of momentum, magnitude is amount, but opposite in direction. After the 2 skaters push off one another, what is the ratio? Actually, I changed that question a little bit, so it's not really a ratio, it's just which one's greater or larger, or the same, compared to A. So is B bigger than, velocity of B bigger than A? So velocity of B less than A, or are they equal in velocity? Well, it's not C. C would be equal momentums, equal sides of momentum. But what about the speed? Well, since A is a bigger person than B, A is going to need less speed to have the same momentum as B. So B will be going faster. Let's see where that is. Velocity of B is faster than A. So 2 ice skaters that are standing there push apart. Which skater experiences a bigger magnitude impulse? So which one experiences a bigger impulse? Well, impulse is force times time. Well, Newton's third law says the forces are the same, and they touch each other for the same amount of time. So equal and opposite force. A pushes on B with the same force as B pushes on A. So same force, same time. Therefore, they would be equal impulse. D. Which has more momentum, a person walking through the airport or a parked plane? Well, this is a really big mass, and the person's a small mass. But you also need velocity to have momentum, m times v. Since the person's walking, they're going to have a velocity. The airport plane has no velocity, and so it has 0 momentum. And so the person has more momentum. They have velocity. All right, a 1,000 kilogram car traveling at 20 meters per second down the road. So that's got a momentum. How fast would you have to be traveling on your bike, 70 kilograms, to have the same momentum as the car? Or truck, whatever. Car. Well, we need to find the momentum of the truck. Car. So car, P equals mv, which would be 1,000 times 20, or 20,000 momentums. It sounds like the homework problem. All right, I now need the person on the bike, a 70 kilogram object, to have the same momentum. So I want it to have 20,000 momentums, and I want to figure out how fast it needs to go to have that. So P equals mv, but now 20,000 is the momentums I need. The mass is now 70, not 1,000. And so the velocity is what we're finding, v. So I'll just say 20,000 divided by 70 gives me 285 meters per second. All right, number 12 is a graph of a sprinter pushing off the blocks. Looks like B, sorry, not A, who cares about the points? The first little hump graph is his rear foot, So we'll put a big R there. Rear foot, and the larger hump, the next hump, is his front foot. All right, and it looks like it takes more time, goes to a higher force, less time, lower force. So, which foot produces the biggest impulse? Well, impulse is area under the curve. Area under the curve. So which one has more area? Well, that would be that front that front one, but that's not the front. That's the, what is the front foot? Yeah, the front foot there. F. So that would be the front foot. And it has a larger area. All right, impulse is force times time, which is how I get the area of an object. Which foot produces the biggest change in momentum? Well, since impulse is change in momentum, then whatever one has the largest impulse, the front foot, will have the larger change in momentum, or produce the larger change in momentum. And so your front foot is the most important foot when you are sprinting off the blocks. To the right is the force versus time graph. So we've got a bowling ball. A 5 kilogram bowling ball is pushed to cause it to speed up and fly down the lane. We've got 0.01 seconds all the way to 0.5 seconds. So 0.1 to 0.5 seconds there. Actually 0 to 0.5 seconds. Determine the impulse. Well, impulse is force and time, the peak force and the time, so the area underneath here. So impulse is 1/2 peak force times time, and this is particular to this graph, so I'll grab the peak force of 150 newtons, and that was the peak force for a collision that occurred for 0.5 seconds, so 0.5 seconds, half a second to throw that ball. And it gave the bowling ball an impulse of, oh, I gotta do it, 75, half of 75, 150 times 0.5 times 0.5, another 1/2. It would be 37.5. So I get 37.5 momentums. All right, what change in momentum would this cause? Well, impulse is change in momentum. So I know that change in momentum must be 37.5 momentums. Good, just asking the same thing. Excuse me. If the ball was initially at rest in the hand, what would its velocity be? So if it started out at rest, that's an initial momentum of 0 meters per second, not moving. If it gained 37.5 momentums, well, then its final momentum will be 37.5 momentums. And that, I want to just know how fast it's going. So P equals mv. Remember I said we're going to do this equation a lot. P equals mv. 37.5 equals the mass of the bowling ball, 5 kilograms, times its velocity. So I just need to take 37.5 and divide it by 5 to give me velocity. So velocity is 7.5 meters per second. Really? If I divide a 37.5 by 5, I get 7. Okay, cool. All right, so now we get to 2 questions about Newton's third law and impulse and the relationships between them. So I've got a baseball player that hits a baseball with an aluminum bat. And the bat has a much greater mass than the baseball. So, which experience a greater force, the ball or the bat? Well, same. Same force because Newton's third law. And they said Newton's third law is equal and opposite forces. Which experiences a greater impulse? Impulse is 1/2 peak force times time. Well, since it's the same force, Newton's third law, and the same time of impact, because they have to touch each other the same amount, it will be the same amount of impulse, the impulse there. Which experiences a greater change in momentum? Well, impulse is change in momentum. So if I have the same impulse, then I'm going to end up changing the momentum of each of the objects the same. Okay, which experiences a bigger change in velocity? Well, since it's the same momentum, and momentum is m times v, if the change in momentum is the same, then the one with the smaller mass will have the larger change in velocity, so that's going to be the ball. All right, same sort of idea. I've got two cars traveling the same speed in opposite directions. They collide. One has a 1,000 kilogram, we'll call that one moving to the right, 1,000 kilogram car, and then a 2,000 kilogram car. Which car experiences a greater force? Same force, as stated above, Newton's third law. Which car experiences a greater acceleration? Well, acceleration is the change in velocity, so the same force will cause a smaller mass to accelerate more than a larger mass, F equals ma, or actually I guess it'd be acceleration equals F over m. So same force, the smaller the m is, the bigger the a. So the smaller mass. That would be the first car, which we call blue car. Which car experiences a greater change in momentum? Well, change in momentum is a change in velocity since the mass doesn't change, so the one with the larger change in velocity. Oh, sorry about that. Nope, I got it. You got me. Almost got me. Greater change in momentum will be both the change in velocity, but mass needs to be included. So even though the blue car has a large change in velocity, its momentum's only 1,000, so it doesn't change its momentum any more than the 2,000. It goes smaller change in speed, but a bigger mass. Momentum is mass and velocity, so you have to take into account both. And once again, force and time on the same one is impulse, and thus the same change in momentum. So same change in momentum and a greater change in velocity. This is where I was going. Greater change in acceleration would mean a greater change in velocity, so it's the blue. All right, then we get to our last two problems, which is our last three problems, which are our calculation-based collisions. So the first one here, JW rolls a 7 kilogram bowling ball down the alley, league championship. One pin is still standing, and the ball hits head on. So the pin's still standing, and it hits it with 9 meters per second. Afterward, the 2 kilogram pin acquires a forward velocity of 14 meters per second. What's the new velocity of the bowling ball? So here's what we got to draw it. Remember I said I'm going to give you a picture on the board that gets you started. So before the collision, this would have been on the board. Bowling ball moving with a velocity and a bowling pin I really should just draw it as an oval. A bowling pin not moving. So there's the drawing that would be on the board. You need to put the numbers on there. So a 7 kilogram bowling ball moving at 9 meters per second hits a 2 kilogram bowling pin not moving. All right, after the bowling ball is going to keep moving forward, probably. I don't think it's going to bounce off of a bowling pin. It's going to keep going. But our number or velocity will tell us that. And we'll have a bowling pin that shoots forward, and we said that it shoots forward at 14 meters per second. So this is still 2, this is still 7, and we don't know this velocity. B, calculate the final velocity. A will be traveling. Well, you can see I just copy and pasted from the example there. So let's make that pen. All right, calculate the final velocity. The pin will be traveling after the collision. That Abe is the next question there. So I need to find the momentums. So I can't just jump right to velocity. I need to find the momentum of each thing and say that the initial momentum is equal to the final momentum. So 9 times 7 is 63, but I'll check it on the calculator. So 63 momentums from the bowling ball, 0 from the pin. So 63 plus 0 must equal my bowling ball's final one, which I don't know, but I'm going to call it P, plus my momentum, 2 times 14 plus 28. So I know 63 plus 0 needs to equal something plus 28. Well, 63 minus 28 is 35. So the bowling ball still has 35 momentums left after the collision. So how fast is that? Well, P equals mv. So 35 must equal the mass of the bowling ball, 7, times its velocity, v. 35 divided by 7, so it slows down to a velocity of 5 meters per second. All right, 17. We did this as a warm-up in class, but I'll go through it one more time. Again, you'll have a picture to start with, so you would have had Abe running to the right, Biff running to the left, and I would have given you that first start up there. Now you would need to add the numbers, so I've got Abe, 45 Abe, and a 90 Biff, running at 2, Abe running at 2, Biff running at -6, negative because it's in the negative direction. And then after the collision, Abe is going some direction, and Biff continues forward. Again, 90 and 45 each. So I don't know Abe's velocity, but I do know that since Biff keeps going at -1, slower, but still going that way, that he's going to knock Abe backwards. D, calculate the final velocity of Abe. Well, again, I need to calculate the momentum of each of these objects first to find the momentum of Abe. So 45 times 2 gives me 90 momentums. 90 times -6 gives me -540 momentums. And so if I add those up, 90 plus -540 gives me -450. I'll do that again down here. 90 plus -540 will give me -450 momentums. So that is the initial momentum of Abe and Biff together, the total momentum, and that needs to be the same after they collide. So that's going to equal, don't know Abe's momentum, P, plus Biff's final momentum, 90 times -1, or -90. So -450 needs to equal P plus -90. So to solve for P, I'll just add 90 to both sides since it's negative, plus 90, and I get P equals -360 momentums. All right. Well, then I need to find I need to find how fast Abe's going. So I know Abe's momentum, but I need to know his velocity for that. So P equals mv. We're doing it a lot. P equals mv. 360 needs to equal Abe's 45 kilograms times his velocity. If you do that math out, velocity comes out to be -8 meters per second. Negative makes sense because he's moving backwards. All right, last question. Anthony and Sissy are roller skating. So again, I will give you a picture. So I've got, actually for this one, I'll probably give you both pictures. I'll probably just give you the picture. So I've got person here, roller skating. We'll figure out which one is it, each one. All right, so since you're not getting credit for drawing on this one, I will give you the picture for this. And then afterward, you've got, okay, so anyway, Anthony and Sissy are roller skating. While 75 kilogram Anthony roller skates backwards at 3 meters per second, 60 kilogram Sissy jumps into his arms with a velocity of 5 meters per second. So the backwards is a little weird. I guess this is Anthony here moving backwards, but we'll say moving to the right.